Hi, my name is Kawthar Shafie Khorassani, and I will be presenting our work on adaptive and hierarchical large message all-to-all communication algorithms for large-scale dense GPU systems. In this work, we propose optimized designs for personalized and non-personalized all-to-all communication for GPU systems. Here's a brief overview of the outline of this presentation. I'll first delve into the introduction and motivation behind this work. Then the talk will be split into two sections, first discussing non-personalized all-to-all, delving into the current state of the art, the proposed solution, followed by a performance evaluation, both at the benchmark and at the application level. And then the same outline will also be followed for personalized all-to-all operations. Then I'll conclude and discuss some future work related to this topic. So in recent years, we've been seeing an increased deployment of large and dense GPU systems becoming more prevalent in high-performance computing through systems like Summit, Sierra, Lassen, ABCI, and so forth. And these systems have thousands of GPU nodes with high-speed interconnects. In this paper, we'll look at systems with dense GPU configurations, and that growing density of GPUs within a node is a result of GPU interconnects like NVLink becoming more available and optimized. And this growing trend makes it more important to ensure efficient data movement between GPUs in order to run HPC applications at scale. In the past, plenty of research has been done on optimizing point-to-point and collective communication, such as all-reduce and broadcast. However, with the growing need for optimized all-to-all communication, which is being used in various things like performing matrix transposes or FFT, so fast Fourier transform, in scientific applications, or also more recently in performing model parallelism for deep neural network training on GPU clusters. This makes it vital to have an in-depth study of all-to-all MPI communication operations on various systems, and then also to adapt new designs that enhance performance while utilizing available interconnects and new architectures for next-generation dense GPU systems. In this work, we explore the challenge of designing hierarchical, adaptive, and high-utilization personalized and non-personalized all-to-all communication algorithms on dense GPU systems. So we first do a comprehensive evaluation of the existing all-to-all and all-gather communication algorithms within the state-of-the-art MPI library. And then we propose new all-to-all algorithm that decomposes the pairwise communication pattern and utilizes the interconnects such as NVLink available between GPUs to minimize the link idle time. We also propose an advanced hierarchical algorithm that will achieve high overlap between inter and intra-node communications to improve performance of all-to-all and all-gather communication. And then we conduct performance evaluations of all-to-all collectives with the proposed designs in various CUDA-aware communication libraries like MVAP-H2 GDR, Spectrum MPI, Nickel, and OpenMPI, using microbenchmarks, a 3D FFT application kernel, and KFAC distributed DNN optimizer. So the image on the left shows the hardware configuration of the Lassen system, which is number 17 on the list of top 500 supercomputers, and then the number 2 Summit system on the right. In this work, we look at these two systems as dense GPU systems used to evaluate the performance of existing algorithms and for motivation to propose new algorithms according to this architecture. And these systems are both powered by Power 9 systems and Volta V100 GPUs. NVLink is an interconnect provided by NVIDIA that's available between GPUs and also available between CPU and GPU. The XBus is an IBM interconnect between Power 9 CPUs. And the Mellanox InfiniBand network connects nodes via dual rail EDR for these clusters. So we utilize the high bandwidth NVLink interconnects make available on these systems to optimize the communication of all-to-all collectives. And one thing to note here also is on Lassen you have 4 GPUs per node, so that's 2 GPUs per socket, while on Summit you have 6 GPUs per node, so that's 3 GPUs per socket. Next, we'll delve into non-personalized all-to-all communication. We'll go over the state of the art with existing designs, discuss their limitations, propose new designs, and show an application level and benchmark level evaluation of the new designs compared to the state of the art. All right, so non-personalized all-to-all is often referred to as all-gather. So on this slide, we're going to discuss the existing algorithms for MPI all-gather. MPI all-gather, first of all, is an MPI collective communication pattern that acts sort of as a combination of MPI gather followed by a broadcast operation. So all the processes gather the data from every other process in rank order. And then at the end of the operation, every process would have exchanged data with all the other processes. So these are some of the various existing all-gather algorithms within the state-of-the-art MPI library. And the difference in these algorithms, as shown in these figures on the right, is how the communication is scheduled for each of them. So first of all, with a direct algorithm, as its name implies, it's a direct approach where the ranks directly communicate their information to each other. So it would be just a direct MPI gather followed by an MPI broadcast. And then we have the Bruck algorithm. And for example, in this recursive doubling algorithm, this is what we would call a hierarchical or a tree-like approach. So in the first step, process 0 and 1 communicate their information with each other, 2 and 3, 4 and 5, so forth. And then in the next step, it moves on to process 0 and 2. And in step 3, it would be process 0 and 4. And this is on a 2-node example with 4 GPUs per node. So in step 1 and step 2, this would be intra-node communication, whereas in step 3, it would be going across the node. And then in a ring approach, just like this, this is the pattern that would be used, process 1 to process 2, process 3, and so forth. So in proposing a new design, we would have to note that these existing designs don't have high link utilization with the way they're scheduled. So for example, the NV-link between GPUs may be idle at certain points in the communication while the communication bottleneck happens at the IB layer. And they do not have overlap of utilizing a two-level approach that would in some way overlap the internode and the intranode communication. So going right into the proposed design for MPI all-gather. The proposed design here would aim to improve the performance of all-gather communication algorithms for dense GPU systems through utilizing the NVLink high bandwidth interconnect between GPUs. And that would have faster communication of large data in order to overlap or hide intranode communication by overlapping it with the internode communication. So on large-scale dense GPU systems where the GPUs are connected by NVLink on a node, and that was shown in the topology of both the Lassen and the Summit system, a different communication pattern can be implemented for intranode as opposed to internode. So this is a two-level approach where an intranode has a different implementation and then internode has a different implementation. So over here, this is what would be happening intranode. So this represents node 0, which has 4 GPUs on the node, and we would define a node leader, which would be GPU 0. So on node 1, the node leader would be GPU 4. On node 0, within the node, you have GPU 0 doing a direct broadcast of its data and a gather of the data from the GPUs on the node, while simultaneously GPU 0 is communicating data to GPU 4. So the only GPU that is communicating across the node is GPU 0. So it's scheduled such that this communication is happening at the same time as this communication going across the node. And this would have a tree-like approach, a hierarchical approach at internode, whereas it's a direct approach at internode, whereas it's a direct approach at intranode. So in this slide, we show the experimental setup. We use the OSU micro benchmark suite to evaluate performance, and the different communication libraries we used are MVAP2GDR, OpenMPI, Spectrum MPI, and Nickel, and these were the versions that were available at the time we did our evaluation. So our proposed designs are implemented within the MVAP-H2 library. In a quick overview of the MVAP-H2 library, there are different libraries optimized for the CPU or the GPU, and it's a high-performance open-source MPI library with support for different interconnects. But we specifically use the MVAP-H2 GDR library. So going into the benchmark level evaluation of AllGather, we did a performance evaluation of the existing AllGather algorithms compared to our proposed designs on the Lassen systems, ranging from 16 GPUs, so that was 4 nodes with 4 GPUs per node on Lassen, up to 64 GPUs, so that's 16 nodes with 4 GPUs per node. And we compared our proposed design with recursive doubling, Bruck, ring, and direct. And then these percentages on each of the graphs represent the optimization from the best algorithm, so the best performing algorithm compared to our proposed design. And at a large scale, we were able to, at like 4 megabytes and beyond, we were able to show improvements with our designs. So utilizing the NVLink for larger message transfers. And then we also did a benchmark level evaluation showing smaller scale, and this was intended to show the adaptive approach where we optimize the library to select the best algorithm for each message size. So compared to different state-of-the-art communication libraries, and we also compared to MVAP-H2 GDR 2.3.4 versus our proposed adaptive approach of MVAP-H2 GDR, where it would select the best algorithm at every message range. And we evaluated this on 128 GPUs on the Lassen system. So this is for smaller message range, and this is for a larger message range. And then we also did an application level evaluation of AllGather. We used the distributed KFAC for deep learning training. This application utilizes MPI AllReduce and MPI AllGather operations, and these are the two collective operations that take up some time. So we evaluated performance with our optimized MPI AllGather designs versus state-of-the-art, and the results are shown as an average total time for each epoch of training on ImageNet. So with different number of GPUs, 16, 32, 64 versus 28, we were able to show up to 8% improvement against the best performing communication library. So now we're going to delve into the personalized all-to-all proposed designs and evaluation. All right, so looking at personalized all-to-all, these are the existing algorithms for within the state-of-the-art MPI libraries. Now, first of all, personalized all-to-all, which is also referred to as MPI all-to-all, is similar to MPI AllGather in that all of the processes are sharing data with each other. However, every process sends distinct data to other processes, making all-to-all a personalized collective communication pattern. So every process will send a different chunk of data to every other process. This makes the two-level overlap approach where you're scheduling it so that other GPUs can share the entire information within the node with other nodes a little more difficult compared to MPI AllGather. So for the sake of time, I won't go into details of all the existing algorithms, but one algorithm that does come up in the designs as well is the pairwise algorithm. And this is how the pairwise algorithm would be implemented on a 2-node example, so 4 GPUs per node. It would be the number of GPUs in the communication, so there are 8 GPUs minus 1 steps. So it would take 7 steps for 8 GPUs, where in step 1, process 0 and 1 communicate, and so forth, and then step 2, process 0 communicates with 2, until process 0 has communicated with every other process. So this is a step-by-step demonstration of the proposed algorithm for all-to-all, for personalized all-to-all. So first of all, in systems with asymmetric interconnects, the traditional all-to-all algorithms can easily have contention on the slowest link. So if all the GPUs within a node are performing internode communication over IB, the high-speed NVLink and the PCIe may remain idle during this process while the contention happens over IB. And that makes it hard for scaling to all to a large number of GPU nodes because overall performance and link utilization can be low. And in this scenario, even though the amount of data transferred over the links is the same, the performance can vary depending on how you schedule the communication. So in this all-to-all algorithm, we also show a two-node example where there are 4 GPUs per node. And we're showing how we overlap the communication and try to implement a two-level approach to utilize the NVLink and ensure it's not idle the entire time. So in this step, the node leader is GPU 0, and over here the node leader is GPU 4. So GPU 0 and GPU 1 will be communicating their data to each other as GPU 0 and other GPUs on the node will be communicating within the node over NVLink with each other, while GPU 0 has already initiated sharing the data from GPU 0 related to GPU 4 through 7 to node 1. And same thing is happening on the other nodes. So while GPU 0 is attempting to share the relevant data for 4 through 7, GPU 4 is also sharing GPU 4 through 7 data to GPU 0. And then in the next step, across the node, you would want to gather GPU 1's data to the leader for internode communication. So the relevant data from GPU 1 that would have to be shared, that would have to be scattered amongst GPU 4, 5, 6, and 7. And then in step 2, that's what would be happening. You would be sending the next chunk of data from GPU 2. So GPU 2's data that's relevant to node 1. And the same thing would be happening on other nodes. And this internode communication would be a pairwise approach. So node 0 and node 1 are communicating now, and after that it would be node 0 and node 2, while node 1 and node 3 are implementing the same setup. And when GPU 0 receives the data from GPU 4, it scatters that amongst the GPUs within the node. And same approach in step 3. This is a high-level representation of what it would look like on an 8-node example. This is with 32 GPUs, 4 GPUs per node. So in the first step, since we have a pairwise approach, the node leaders on node 0 and 1 are communicating, node 2 and 3, and so forth. And then in the second step, it would be node leaders of 0 and 2, while 1 and 3. And this pattern continues to implement a pairwise approach across all the nodes. So over here we show a benchmark level evaluation of all-to-all with existing algorithms compared to proposed designs on the Lawson system. We were able to scale from 32 GPUs on 8 nodes to 256 GPUs on 64 nodes, and for a message range from 64 kilobytes and beyond, we were able to show improvements. And then we also did a benchmark level evaluation of the entire message ranges to show an adaptive approach being used in all-to-all. Same thing that we did with all-gather. We evaluated this on 128 GPUs to show that we were selecting the best algorithm possible at every message range. And then we did an application level evaluation of all-to-all. We evaluated personalized all-to-all algorithms for a 3D FFT application kernel on the Lawson system. And this kernel imitates the FFT computation of an application requiring MPI all-to-all communication. We were able to show 15 to 20% range improvement of our proposed designs over existing designs within the library. And we were able to scale this up to 256 GPUs. Finally, we'll conclude this work and discuss some future work. So in this work, we evaluated personalized and non-personalized all-to-all collective communication on dense GPU systems, and we conducted a thorough study of the existing designs and compared to state-of-the-art designs with our proposed designs. And then we also evaluated benchmark level and application level performance. The future work that we can apply to this is to evaluate our proposed designs using different applications that more heavily rely on all-to-all and specifically personalized all-to-all. And then also evaluate on different systems, so like DGX systems with 8 GPUs per node, which are double the density of the Lawson system, for example, or on systems where the GPUs are entirely connected by NVLink, so there is no XBus contention. Thank you, and feel free to refer questions to me at this email.